So the general trend for single displacement reaction is that on the left side, on the reactant side, you've got a compound. So in this case, we've got A and B that are chemically linked together, plus you've got an element that's by itself. And if this reaction does take place, the C and the A will switch spots, right? So if you take a look on the product side, A is the element that's by itself, but B and C are now chemically linked together. Now, whether or not this reaction actually takes place or not is something that we have to find out. We have to think about depending on the elements that we're given. And we have to refer to something called the activity series of metals. And this takes place if you've got metals in your reaction, you have to refer to your activity series of metals. There is another activity series for halogens, which we'll talk about towards the end of this video. But essentially, what the activity series of metals is, it's a list of metals that are arranged from most reactive, so lithium, up here, and least reactive, gold, down here. And what you're trying to do is you're trying to compare the element that's by itself to the element that's in the compound, right? The metals that are involved in that single displacement reaction, the metal that's by itself, you want to compare its reactivity to the metal that's in the compound. And if the metal that's by itself, if that is more reactive, that reaction is going to take place. It's able to switch places with that metal in the compound. So we'll take a look at what this looks like in terms of a reaction. So the first type of single displacement reaction that we're looking at is we're going to compare two different metals displacing another metal. So as I mentioned here, I've got one element, magnesium, and a compound, zinc chloride. What I'm going to do is compare the magnesium with the zinc on the activity series. So the magnesium is the element that is, or the metal that's by itself. I'm going to designate that by drawing an arrow. And zinc is the metal that is in the compound. So if you compare these two, magnesium is much more reactive than the zinc, which means this reaction is going to take place. You want the metal that's by itself to be higher up on the activity series. And because this does take place, now instead of the magnesium being the element that's by itself, on the product side, zinc is going to be by itself. And when I say by itself, I just mean that it's not chemically bonded to anything, right? It's just zinc. And now my compound is magnesium chloride. And I'm going to do this once. So whenever you're trying to figure out the products of a reaction and you've got to make a compound, you have to go back to its charges, right? So magnesium has a charge of +2, chlorine has a charge of -1, and we have to crisscross this so that it gets MgCl2, right? So MgCl2 is my compound here. Okay, and that is already balanced. In case it wasn't, I would have to balance it, but it is balanced, so I'm good to go here. All right, so here's another example, FeSO4 plus Cu. So in this case, I've got iron sulfate as my compound and copper as the metal that's by itself. Let's compare the two. So copper and iron. So copper is the element or metal that I have by itself, and iron is the metal in the compound. And because the metal that's by itself is not more reactive, it's less reactive than the metal in the compound, this reaction does not take place. I'm going to write no reaction. And this is what you have to do whenever you're in a situation where you see that this reaction cannot take place. Copper is not more reactive than the iron, that this reaction will take place. So, and in the product side, I would just write no reaction. All right, why don't you try it? So pause the video, see if you can give this a shot, refer to your activity series in your notes. So you're comparing, in this case, iron as the metal that's by itself, but copper as the metal in the compound. And press play whenever you're ready. So iron is the element that's by itself, so I'm going to put an arrow there, and copper is the metal that's in the compound. Now in this case, iron is more reactive than the copper, which means that this reaction will take place. So on the product side, I've got copper that's by itself, and I've got iron and sulfate forming a compound. And because iron is a transition metal, I have to be told what the charge is. And it's just written here, iron has a charge of +3. So again, I have to go back to my crisscrossing, right? So I have to refer to my charges before I predict what the chemical formula of something is going to be. Fe2SO4 3. That's what I'm going to write here. There we go. This is not balanced, so I am going to balance it by putting a 2 here and a 3 here and a 3 here. So that is all balanced there. All right, moving on to the next example. Again, do the same thing. Pause the video, see if you can give it a shot, and then I will take it up. I'm comparing copper as the metal that's by itself and silver in the compound. Copper is down here, silver is down there. So yes, copper is more reactive, which means this reaction will take place. So silver is going to be by itself, and copper has a charge of +1, and nitrate has a charge of -1. CuNO3 is the compound that is going to form. This is already balanced, so I don't need to do anything else. That's it. So this is how you would compare, or you would write the products for if your single displacement reaction involves the comparison of metals. Now we're going to take a look at a second type of single displacement reaction that involves hydrogen. And I don't know if you've noticed this already, but on the activity series, you've got hydrogen on there. And hydrogen is on here so that you are able to predict whether or not metals can react with hydrogen or take places with hydrogen, specifically in acids or in water. So there are two different rules here. So the first one is that any metal that's higher than hydrogen on the activity series, so all of these ones right here, they can take place, or they can switch places with hydrogen if it's in an acid. So if it's metal plus acid, that metal, and it's one of these ones here, that reaction will take place. And we'll take a look at a few examples. If that's confusing, that's okay. When you see the example, it might make a little bit more sense. The second rule is that only these metals, the ones up here, sodium to lithium, only these ones are able to displace hydrogen from water. So if the hydrogen is in an acid, and that's that single displacement reaction, all of these metals above hydrogen can do that. But if it's a single displacement reaction with a metal and water, only these metals can displace that hydrogen. Let's take a look at a few examples. So I've got, in this case, Mg plus H2SO4, magnesium plus sulfuric acid. So I'm comparing whether or not magnesium will be able to displace this hydrogen from this acid. So I'm going to do the exact same thing actually. So magnesium is the metal that's by itself. Hydrogen is all the way down here. So magnesium, because it's higher than that hydrogen, this is a reaction that will take place. So when I'm doing that, I have hydrogen that's going to be by itself. And remember that hydrogen is a diatomic molecule, which means that when it's by itself, it's going to have a 2 there, right? So H2 plus, and my new compound is MgSO4, magnesium sulfate. And the chemical formula for magnesium sulfate is MgSO4. And that has taken into account the charges for magnesium and sulfate. Mg has a charge of +2, sulfate has a charge of -2, so now we have MgSO4. And this is already balanced, so I don't need to balance it any further. This is it. Let's try a few more. So in this case, I've got sodium plus water. So I'm trying to see if sodium will be able to displace the hydrogen from water. And because sodium is right here, yes, it does, right? It says that anything from sodium to lithium can displace hydrogen from that water. So this is true. Now, how do we figure out the products? It helps if you have, when you look at water in these types of reactions, as HOH, right? And when you're able to separate water as H and OH, it helps you to see what the Na is going to switch places with. So Na and the H are going to switch places. So one of my products will be NaOH, and my other products is H, that's by itself, but remember, because it's diatomic, I'm going to put a 2 right there. And now this is not balanced, but I'm going to make sure that it is. So if I put a 2 here and a 2 here and a 2 here, I think that should be balanced. So 2 sodiums, 4 hydrogens, 2 oxygens. So that is balanced there. All right, let's compare copper and hydrogen here. So this is hydrochloric acid. Let's see if this reaction takes place. Copper is the element or the metal that's by itself, and hydrogen is in the compound. So notice here, copper is a metal that falls below hydrogen on the activity series, which means that this is no reaction. I'm just going to write it as Nr, which means that this reaction will not take place. And lastly, I've got cobalt and water. I'm comparing cobalt and the hydrogen here. So cobalt is down here and hydrogen is here, right? So cobalt can displace hydrogen from acids. However, it does not fall into the few metals that can displace it from water. So because that is the case, this is no reaction. All right, that was our second type of single displacement reaction. And now we're going to move away from metals and move towards halogens, right? So in this case of single displacement reactions, the element that's by itself is a halogen, and we're trying to figure out if that halogen is going to displace a halogen from a compound. And if that's the situation that you're in, you have to refer to the activity series of halogens. So it's works the exact same way. You've got the most reactive elements at the top and the least reactive at the bottom. So I think you should be able to, based on your understanding of the activity series of metals, you should be able to try and do this. So if you want to pause and take a shot at it, feel free to do that. But essentially, you're just comparing the element that's by itself, the halogen that's by itself, and the halogen in the compound. So Cl and Br. So Cl is the halogen by itself, Br is the halogen in the compound. And when I'm doing that, I know that this reaction will take place because Cl is more reactive. So Br is going to be by itself, and remember, it is a diatomic molecule, and you have KCl that's going to be the new compound. That is not balanced yet, but it will be soon. So that is the balanced equation for that one. Let's take a look at another example. So this time the roles are kind of reversed. So I've got Br as the halogen by itself and Cl as the halogen in the compound. So Br is down here and chlorine is up here. So this means that this reaction cannot take place. The halogen by itself is not more reactive than the halogen in the compound. So I'm going to put Nr right there. And that is pretty much it for the 3 different types of single displacement reactions. Hopefully you're able to predict the products for all 3 of these with reference to the activity series.